12 feet of reinforced concrete. Steel rebar every 6 inches. Designed by the best engineers in Europe to withstand a direct hit from any weapon in existence. The Germans believed these structures were eternal. That nothing dropped from the sky could ever reach what was hidden inside. And then a single 500-pound bomb fell, punched through the concrete like paper, and detonated within. In less than 3 seconds, a fortress became a tomb. This is the story of the bunker buster, the weapon that made nowhere safe, and forced engineers to completely rethink what a bomb could be. June 1940. Along the coast of occupied France, German engineers begin pouring concrete on a scale never seen before. These are not ordinary buildings. They are submarine pens, colossal shelters designed to house and protect U-boats from Allied bombing. The specifications are extreme to the point of obsession. Walls 15 feet thick. Roofs 12 feet thick. Steel reinforcement laid in a grid so dense that a knife blade cannot slip between the bars. The concrete mixture itself is experimental, using special aggregates and chemical hardeners that make it far stronger than anything used in civilian construction. When the first test section cures, workers attempt to demolish it with jackhammers. The jackhammers break. The concrete does not even crack. Photographs of the construction eventually make their way to London. A British intelligence officer places them on a table in a quiet meeting room at the Admiralty. The planners lean in, studying the images, and slowly realize the scale of the problem. U-boats are sinking Allied shipping faster than it can be replaced. Britain's lifeline is being severed at sea. The only way to stop it is to destroy the submarines at their bases. But these bases are immune. The Royal Air Force has already tried. In August 1940, 50 bombers attack a partially completed submarine pen at Brest. Over 200 bombs fall. Most miss. Those that hit detonate on contact, leaving shallow scars barely inches deep. The Germans repair the damage in 2 days and continue pouring concrete. The British return with heavier bombs. 500-pounders. Then 1,000-pounders. Nothing changes. The bombs explode on the surface, their energy venting harmlessly into the air. The concrete absorbs the shock like a mountain absorbs rain. By late 1940, 6 massive submarine pens operate along the French coast, each sheltering up to 20 U-boats, completely untouched by air attack. Allied analysts calculate that at the current rate of shipping losses, Britain will be starved into surrender within 18 months. Something has to change. That change begins with one man, Dr. Barnes Wallis. Already famous for designing the geodetic airframe of the Wellington bomber, Wallis is brilliant, obsessive, and deeply unconventional. When he is shown photographs of the submarine pens, he does not see an impossible problem. He sees a solvable one. While other engineers argue for bigger bombs, Wallis quietly studies physics. He explains his insight to skeptical officers in simple terms. The problem, he says, is not that the bombs are too small. It is that they are being used wrong. Every bomb the RAF drops detonates the instant it touches concrete. 90% of the explosive energy is wasted, blasting outward into the air. What is needed is not a larger explosion, but a smarter one. A bomb that survives impact, penetrates the concrete, and explodes inside the structure, where all that energy has nowhere to escape. The question is how. When an object strikes concrete at high speed, enormous forces are involved. Deceleration can reach thousands of times the force of gravity. Brittle objects shatter. Soft objects flatten and lose momentum. Wallis realizes that penetration is not about sharpness or brute strength. It is about how energy is delivered, how fast, how concentrated, and how well the object holds together under stress. He begins experimenting. A concrete test pad is built to match German specifications. Wallis drops steel cylinders, pointed rods, hardened shells. Nothing works. Some dent the surface. Others snap or detonate prematurely. Month after month, failure follows failure. Colleagues dismiss the project as a waste. But Wallis learns from every test. Concrete can absorb almost any force if it has time to distribute the stress. But if energy is delivered faster than the material can respond, fractures form. And once a fracture exists, penetration becomes possible. The breakthrough comes in early 1941. Wallis designs a bomb casing shaped not like a cylinder, but like a streamlined teardrop, with a blunt, hardened nose. Counterintuitive, but deliberate. A pointed tip concentrates stress too narrowly and snaps. A blunt nose spreads the impact through the casing while still focusing force onto a small circle of concrete. The casing is forged from a special steel alloy, heat-treated to resist deformation. 3 inches thick at the nose, tapering toward the tail. The bomb weighs 500 pounds, but most of that weight is steel. Only 200 pounds is explosive. This goes against every existing bomb design philosophy, but Wallis understands that where the explosion happens matters more than how big it is. Then comes the fuse. A normal impact fuse detonates instantly. Wallis needs a delay measured not in seconds, but fractions of a second. Inside the bomb nose, he installs a heavy steel weight held by a spring. During free fall, it remains still. On impact, inertia slams it forward with tremendous force, triggering a mechanical clockwork delay precisely calibrated to 0.08 of a second. Just long enough for the bomb to punch through concrete. Not long enough to overshoot the target. In tests, the bomb strikes the concrete pad, disappears inside it, and then detonates. The explosion is trapped. Shock waves reflect off the surrounding concrete, amplifying pressure. The roof collapses inward. When the dust settles, the structure is gone. Silent officers stare at the crater. Then applause breaks out. Wallis has cracked the unbreakable. Production begins immediately. But Wallis thinks bigger. If this works at 500 pounds, it will work at 1,000. At 2,000. Then he proposes something extraordinary, a 12,000-pound bomb. His superiors call him insane. No aircraft can carry it. Wallis replies calmly, then build one that can. For now, the 500-pound Penetrator goes to war. In September 1941, Lancasters attack the submarine pens at Brest. Bombing accuracy is poor. Most bombs miss. But 14 hit. The Germans hear the familiar impacts and relax. Then the roof explodes from below. Concrete collapses. Steel rebar falls like spears. Submarines are crushed. Flooding follows. Repairs take weeks. Worse than the damage is the realization, the pens are no longer safe. Germany responds by building thicker roofs. Britain responds by dropping heavier bombs from higher altitudes. An arms race begins, and the bombs are winning. Inside these weapons is another secret, Torpex. A powerful, stable explosive mixture of RDX, TNT, and powdered aluminum. Stronger than TNT, yet resistant to shock. It survives the violent impact without detonating prematurely, then unleashes devastation exactly when intended. By 1942, an entire family of bunkerbusters exists. From 500 pounds to the massive Tallboy and Grand Slam bombs that create underground earthquakes. Rail tunnels collapse. Viaducts shatter. Submarine pens crumble. German engineers are forced to abandon centralized underground production entirely, dispersing factories across the countryside and slowing output at the worst possible moment. Each bomb begins its life in factories staffed largely by women, working night shifts under constant risk. Steel casings are forged, heat-treated, hardened. Torpex is poured with extreme care. Fuses are tested again and again. Accidents happen. People die. Production never stops. One bomb, serial number MC8847, leaves Manchester in October 1943. Weeks later, it falls from a Lancaster over Dusseldorf. It accelerates to nearly 800 miles per hour. It punches through earth, rock, concrete, steel. The fuse ticks down. The explosion rips the heart out of an underground factory. 6 months of production vanish in seconds. German engineers inspect the ruins and realize there is no defense. After the war, Wallis refuses to design weapons again. He is haunted by how his ideas were used. The same engineering that cracked submarine pens also destroyed cities. That contradiction never leaves him. But the principle he discovered endures. Modern bunker busters still follow his blueprint. Hard casing. High velocity. Delayed detonation. Precision over power. The final truth of the 500-pound bunker buster is not just destruction. It is inevitability. Any fortress can be cracked. Any defense can be defeated. Given enough understanding of physics, nothing is permanent. Wallis proved that in 1941. And every bunker-busting weapon since is just another confirmation of the same terrible truth. Precision always wins.